Hey everyone, Shadow Rockets here, and today I figured I would do something a little bit different, and that is because I want to actually go in and kind of talk about the physics that we're going to talk about tomorrow in my effed up physics episode. So without further ado, I kind of want to just get right into it. This is going to be kind of an introduction to physics too. So if you want to just kind of refresh yourself, or if you're looking to take physics, this would be a good one to watch. So, I'm sorry that I'm not going to have any gameplay for this episode. This is pretty much just going to be purely physics-based. So, let's go ahead and just start with simple things like distance, or displacement, we're going to call it for this episode. That would be, if this is your starting point, your 0 per se, then we're going to go ahead and travel some distance to this point right here. And this can be 1, or 1 meter, we could say, to give it some sort of actual value or logical numerical value, I guess you could say. So there we go. So now we have a displacement of 1 meter. This 1 meter's displacement is just from this distance to this distance. Now, the thing that kind of tricks people up is there is actually a difference between displacement and distance traveled. So let's say this is your 0 point. Again, you go out to 1, and then you go back to 0, or your 0 point anyway. The distance you traveled would be the 1 here and the 1 here, making it a distance of 2 meters. The displacement, however, is your distance from your starting point. So your displacement is 0. So that's just something to kind of look out for whenever you're starting your physics world. But anyway, we're going to use this synonymously. We're not going to actually go back to our starting point in any of the math we're doing today or tomorrow. So I'm going to use these words interchangeably. So in essence, I don't want to kind of give away what I'm going to talk about tomorrow. But I'm essentially just going to treat this as x. And now, x is going to be your displacement from your start. We're going to actually, let's go ahead and just set x as displacement, not necessarily distance. But it's going to be, essentially you can write it as delta x. Delta just means the change in distance, so it's going to be your final point, your xf, minus your initial point, xi. And if your initial point's always 0, then it's always going to be xf. You know what I'm saying? So we're going to go ahead and just x equals displacement. And for this, we're going to be using units of meters generally, or you could use feet, meters, feet, inches, centimeters, millimeters, nanometers, whatever. Miles. You do you. So now I want to talk about time. Time, or more so, we're going to use delta t for change in time, again, which will be your time final minus your time initial. And your time initial should just about always be 0. So essentially, we're always going to take this. You can't really go back in time. Technically, there's going to be some interesting physics tomorrow. So just be prepared for this. But technically, you can't go back in time. So we're going to go ahead and just treat this as always 0. And this is always x, or some other time. So when you get, this is in units of seconds also. When you get these two things, you put them together. Essentially, if you have I'm gonna throw in some calculus here, just for the sake of shenanigans. If you have your distance versus time graph, x over t, and let's just say this is your distance is constant for this time. It goes up here. Actually, I kind of don't want to go into that yet. It goes up here, goes over, down, and whatever. So essentially, you're sitting at a distance here. Let's say it's 2. Then you go up to this distance here. Let's say it's 3, and then you go all the way back in less than a second, which wouldn't happen, but whatever. You teleport in this instance, and you just drop down to a distance of 0 here. The derivative, I guess I should probably draw this realistically because you can't teleport. So yeah, it'll be like this, because each change in distance actually has a change in time, because this is time. So this would be like 0 seconds, 1 second, 2 seconds, 3 seconds. So more realistically, this is going to be your case. I guess technically this scale is just much too large if you want to look at it that way. So let's just ignore this one. Sorry about that. That was kind of a bad drawing. I was trying to make it simple on you. But if you take the derivative of this at any given point, that's actually the velocity, meaning that the actual like x over t, or distance per time, or meters per second, is velocity, which is, I'm going to use this as like this little cursive v. Now your velocity, this is probably the most simple form of the velocity that you're going to find. So it's essentially your total displacement over your total time. There are other formulas for this, but in the meantime, this is what we're going to stick with. I'm not really going to go into how the velocity per time graph would look for this specific distance graph or displacement per time graph. I could if you want. We can talk about it another time. But essentially your velocity would be 0 right here because you're not moving for this time, and your velocity would be increasing here. Well, it would be constantly up here, and then it'd be constant down here, unless you had acceleration like that, and then like that for this graph, if this was the same graph. If this was curved, then you have acceleration, and then you're going to have a velocity graph that kind of goes up. So I guess I technically kind of did just tell you kind of their relationship. But anyway, we're going to go into the velocity per time graph, because if you take the velocity, or the change in velocity more so the delta v, to keep this consistent, which is going to be the velocity final minus the velocity initial over the delta t, or the time final minus time initial, that's going to give you your acceleration. It's not the instantaneous one, it's the average one, but that's okay for what we're doing. You can also kind of solve it for, or you could take this apart, I guess, and kind of solve for different velocities at different times if you want. So your VF might equal your VO. I use not here instead of VI. I'm sorry, I'm going to try and keep it consistent. So your VI, what is it, plus A times T. So just to kind of put this together so it looks pretty, VF equals VI plus AT. I keep my pluses straight and my t's curved so that you can tell the difference there. So this is kind of what I want to go into here. I kind of want to just work my way to the acceleration, and that's because we kind of are going to have a partial discussion about g-forces. So what is a g-force? A g-force is the force experienced by one gravity, we'll say, one gravitational unit. So if you're over here, or Master Chief is over here on the Earth, you know, you have all these nice little blobs that are the continents and everything. This is our nice little Earth, and Master Chief is apparently very large, standing on the Earth's surface, obviously not to scale. The gravitational force that he feels pushing down on him on the surface is 1 g-force. We just kind of categorize that because it's as 1 g-force because it's kind of a nice unit for us to use. So if you're experiencing, let's say, 2 g-forces, then you're experiencing 2 times 1 g-force. So 2 times the normal force of gravity. So essentially, if force equals mass times mass times acceleration, F equals ma. Sorry, g is the acceleration due to gravity, but we're not necessarily falling in this situation. You double the force, you can kind of guess what that does to you here. Your mass doesn't change, so your acceleration would have to double. So that's just kind of the idea, the mindset behind what we're getting here, you're going to feel really heavy, essentially 2 times as heavy. So we're going to kind of go into how your body copes with that at some point in time tomorrow. Anyway, friends, I think I've taken up enough of your time for today. If you like this episode, if you want to see kind of more physics in my talks, if you want to, I don't know, give me some questions with regards to physics in games, or if you have any ideas of maybe things I could talk about, definitely feel free to comment below. I'm excited for tomorrow's episode. I hope you are too. Don't forget to like, favorite, comment, and subscribe. Shadow Rockets out.